You ever look up at a plane, just a tiny speck slicing through the clouds, and wonder, how in the world do they know where they're going? I mean, up there are no roads, no street signs, nothing. Well, the answer is this amazing mix of maps, magnets, and some math that's actually way simpler than you might think.
And that right there is the big question, isn't it? We're so used to navigating on a 2D plane with landmarks and signs everywhere. But pilots, they're working in 3 dimensions, often flying over oceans or deserts where everything looks the same for miles and miles. So, seriously, how do they pull it off?
I know. You look at a cockpit and it just seems like this overwhelming jungle of dials, screens, and charts. But it's not chaos, not at all. It's a system. See, flying isn't just about pointing the plane in the right direction and hoping you get there. It's this whole process of planning and constant calculation called air navigation.
So let's dive right in. Section 1, Flying Without Roads. Let's figure out how you even begin to plan a trip when there's no pavement to follow.
It really boils down to 2 key things. First, you've got to plan your route, your point A to point B. But then, and this is crucial, you have to constantly, and I mean constantly, check that you are actually on that route. You have to know where you're going, sure, but you also have to know where you are every single moment of the flight.
All right, Section 2, the pilot's roadmap. So if you don't have roads, what does a map for the sky even look like?
And honestly, the easiest way to think about it is exactly that. It's a roadmap for the sky. It's called an aeronautical chart, and for a pilot, this thing is their absolute best friend. But it's not like your everyday Google Maps. This thing is packed with info about airspace, radio frequencies, mountain elevations, everything you need to stay safe up there.
Okay, so what you're looking at here is a sectional chart. This is the bread and butter, the go-to map for most pilots doing visual flights. And the level of detail is just wild. It's zoomed in so tight you can see individual airports, radio towers, and even the shape of the hills and valleys on the ground below.
Now, if you're flying near a huge, busy city, think New York or LA, you need even more detail. That's where these VFR terminal area charts come in. The airspace around major airports is incredibly complex, with planes coming and going constantly. So you need a map that's super zoomed in to navigate it safely.
And then you have the opposite. For those really long cross-country flights, you've got the World Aeronautical Chart. This is your big picture view. It's way more zoomed out, showing a huge area with less of the tiny details. It's perfect for planning out the major legs of a long journey.
So on any of these charts, the very first thing a pilot does is pretty simple. You take a ruler and a pencil, and you draw a straight line from where you're starting to where you're going. That line, that direction, is called your true course. Easy enough, right? Well, this is where things start to get a little weird. Which brings us to Section 3, Earth's 2 North Poles. Yep, you heard me right. The north on your map is not the same north your compass is pointing to. I mean, think about that for a second. This is the fundamental problem every single pilot has to solve. Your map is this perfect scientific grid of the Earth. But your compass? That's a physical gadget that's just reacting to the Earth's messy, invisible magnetic field. How do you get those two to play nice? Here's the mind-bending part. True north, that's the geographic North Pole, right? The very top of the globe, where all the longitude lines meet. It's a fixed point. But magnetic north, the place your compass needle desperately wants to point, is actually a wandering spot somewhere over northern Canada, hundreds of miles away. And that distance creates an angle of error.
And that angle, that difference between what the map says and what the compass says, is called magnetic variation. What's absolutely bonkers is that this angle changes depending on where you are on the planet. So that perfect true course you drew on your map, it's basically useless until you correct it for your specific local magnetic variation.
So that leads us to Section 4, correcting your compass. Okay, so how do pilots actually make this correction? Well, the solution is surprisingly elegant, and it's been hiding in plain sight on their maps the whole time.
See, printed right on those aeronautical charts are these long dashed lines. They're called isogonic lines. Each line connects points on the Earth that have the exact same magnetic variation. So a pilot just finds the line closest to their route, and boom, it tells them exactly how many degrees off their compass is going to be.
But do you add or subtract that number? Well, pilots have this fantastic little mnemonic they've used forever. East is least, west is best. If the variation is to the east, you subtract it from your true course. If it's to the west, you add it. Simple, memorable, and it works every time.
Okay, awesome. So we've corrected for the Earth's weird magnetic field. We should be all set to go, right? Not quite. There is one more layer of error that we have to deal with.
The airplane itself, the engine spinning, the radios buzzing, all the electrical systems, all of that stuff creates its own little magnetic field right there in the cockpit. And that field messes with the compass, pulling it off by a few more degrees. This error is called compass deviation. And get this, it's totally unique to every single airplane.
To fix this, every single plane has this little card, a cheat sheet, mounted right by the compass. It's called a compass deviation card. It literally tells the pilot, if you want to fly in this direction, you actually need to steer to this number on the compass. So, for example, to fly a magnetic heading of 30 degrees, this pilot actually has to steer a compass heading of 28 degrees.
So, it all comes together in this simple 3-step recipe. First, you start with the true course, that line you drew on the map. Then you apply the local variation, east is least, west is best, to get your magnetic course. And finally, you use the plane's little cheat sheet to apply its unique deviation. The number you get at the end, that's the compass course. That's the number the pilot actually follows on the instrument panel.
Which brings us to our final section, the unseen calculation. Because when you see that plane flying so smoothly overhead, it's so easy to miss all the invisible math that's making that straight, steady path possible.
And that really is the big takeaway. Flying isn't just a physical thing. It's a constant mental exercise. It's this beautiful little system where pilots take a simple line on a piece of paper and translate it into a precise heading, all while correcting for the invisible magnetic forces of both our planet and the very machine they're flying.
It really makes you wonder, doesn't it? Our world is absolutely full of these hidden calculations that guide everything, from the GPS signals that get us to work to the financial markets that run our economy. What other invisible systems are out there, quietly and precisely guiding the things we see every single day?